Alright, welcome back to the third installment if you've watched the first two. If not, welcome. And we are talking about extending trigonometry from only dealing with right triangles to now dealing with oblique triangles, triangles that do not include a right angle, acute triangles or obtuse triangles, and extending our ability to use trigonometric functions on angles that exceed 90 degrees. So, we have talked about the unit circle, which I have up here. So, the radius of a unit circle, because it is a unit, the radius is 1 unit long. So, here's our origin. This point over here would be x is 1, y is 0. The radius is 1. So, last time we talked about how we could find coordinates. So any coordinate in our Cartesian coordinate plane is x, y. Generally, as you know, but because of what we know about right triangle trigonometry, we know that if we have an angle here and our radius is 1, that means our hypotenuse is of length 1. And so SOHCAHTOA tells us that the x coordinate, which happens to be the base of our right triangle, is going to be our adjacent side. So the cosine of theta is whatever that length x is over 1. So we can write that cosine of theta equals x over 1, which of course is just x. So this x could be written as cosine of theta. We'll start that right here. Cosine of theta. Well, what about y? This y direction, that happens to be the opposite side to that angle theta. And we know that sine, SOHCAHTOA, sine is opposite over hypotenuse. Opposite divided by 1. So sine of theta is that y length divided by 1, which is just y. So this y could be written sine of theta. On a unit circle, any point on the circle can be described by cosine of theta, sine of theta. X, y, cosine of theta, sine of theta. Okay, this is cool because although we know about using cosine and sine of theta to find the side lengths that are unknown in a right triangle, we didn't know what to do if we wouldn't have a right triangle. We couldn't possibly have had a right triangle if our theta angle had gone past 90, because no right triangles have any obtuse angles, as you know. Now, we talked about what happens in the second quadrant in the last video. We're going to talk in this video about what happens in the third quadrant. So imagine that instead of having theta be in the second quadrant, or in the first quadrant, it rotates all the way around to the third quadrant. Okay? Theta rotates from the initial ray being the x-axis starting at the origin and rotating more than 180 degrees but less than 270 degrees, so we're in the quadrant 3. Where will it intersect? Well, it will intersect, as we know, at a particular xy coordinate, which is cosine theta, sine theta. Now, this is where it's interesting. You know that in the third quadrant, that x is negative, right? X is to the left of the y-axis, which means x must be negative. That means cosine of theta, x is equal to cosine of theta, so cosine of theta in the third quadrant is going to be negative. And sine of theta is equal to our y dimension, or our y coordinate. So y in the third quadrant is negative because it is below the x-axis. That you're familiar with, but because y is equal to sine of theta, we know that sine of theta in the third quadrant must also be negative. Okay, so this is interesting because in the right triangle trig, cosine of theta, you were used to it being positive because it was telling you about the sides of a triangle. You were thinking about it in terms of a triangle, and we don't have a triangle when we have an angle that's exceeding 180 degrees because the total interior angle of a triangle has to be 180 degrees. So, how are we getting negatives out of this? This is interesting. Well, in a triangle, when we actually have a literal object that's a triangle, all of those sides are of a certain length. They are a distance. And distances can't be negative. You can go in a direction that you describe with negative numbers, but those distances, like say from Des Moines to San Francisco, that's not a positive or a negative thing. It can't be one or the other. It can only be positive. You can only go positive miles to get from one to the other. Doesn't matter what direction you're going. But because we're orienting this in a Cartesian coordinate plane, we're going to now get negative answers because x can be negative when it's going to the left of the y-axis, and y can be negative when it's going below the x-axis. Okay. So, the cosine of this angle theta is going to be negative, which means it's not the length of a side of a triangle, because the length has to be positive. Well, is there a triangle that would have that same value without it being negative? Let's see. If we make a perpendicular line through our point that's not on the x-axis, perpendicular to the x-axis, we now have a triangle right here. Okay, so in that triangle, this distance, this x distance, positive number, is going to be in relationship to this angle, which we will label psi, okay? Angle from the x-axis down to our terminal ray. If we call that the Greek letter psi, then the cosine of that angle is this adjacent side divided by the hypotenuse. The hypotenuse is 1 because it's a unit circle. So the x distance cosine of psi is that distance. Well, this coordinate is negative because we're to the left of the y-axis. So the negative cosine of that angle is going to equal the cosine of the angle we actually want to know about, which is theta. Now, what about the sine? We know that sine of this angle is going to be negative because we're below the x-axis. But in terms of psi, the sine of psi is this opposite side divided by 1, So the sine of c has the same value as the sine of theta, except that the sine of theta is going to be a negative number. So if we make this a negative number, it will be equal. Okay, so we've got now a triangle that we can refer to, even though the angle we're actually interested in is not an angle that can be inside of a triangle. So we're going to be able to extend our trig to angles that are beyond 180 degrees or beyond pi radians. So that angle, C, has a special name. C is a reference angle to theta in the quadrant 3. In quadrant 3. Okay? See this angle from the x-axis down to the terminal ray in a right triangle that we form by dropping a perpendicular line through the x-axis and through to our point on that terminal ray. That angle is the reference angle for angle theta. We can figure out these distances using that reference angle and what we know about right triangle trigonometry, and then we can use what we know about the positive or negative values of x and y in each of the 4 quadrants to come up with a solution to our coordinate for that point. And that's where we want to be. Next video we'll talk about how to find the reference angle in quadrant 4. But in this case, what is the reference angle? If we know theta, well, theta is all the way to here. How are we going to find that? Well, it's all of this minus that 180 degrees. Okay? So we'll write that. C equals theta minus the 180 degrees, or theta minus pi if we're in radians. So that's where we're at. We'll look at quadrant 4 in the next time. Thank you for being with me.